I think we're all settled. Good morning, everyone. I'd like to thank you for joining us again this morning. We will be presenting on the continuous manufacturing of metal organic frameworks, also known as MOFs, for carbon capture. So a little bit about our team. My name is Sara Canzano. I served as the safety lead and business analyst during this project, mostly due to my work at my last co-op and future employer at Rogers Corporation.
I'm Chris Marsh. I was the kinetics lead and IP manager. I have a little bit of background with metal organic frameworks thanks to my research with Professor Sunho Choi here on campus.
Hi everyone, my name is Sevigny. I served as the process design and economics lead, primarily due to the fact that my co-op experience, I've had experience in continuous manufacturing of organic compounds.
Hi, my name is Vozikis. I'm the simulation and materials lead, and like Chris, I worked in Professor Choi's lab synthesizing metal organic frameworks for carbon capture. So over the years, there's been increasing concern about climate change, specifically regarding greenhouse gases. As you can see on the chart here, there's been a dramatic increase in atmospheric levels of carbon dioxide over the last few hundred years. They're currently above 400 parts per million, which is the highest they've been in over 2 million years. So there's some concern with how these will affect our climate and global warming. And there is a move to go towards renewable energy, but that takes time and money and effort, and we're still producing a lot of emissions right now. So we're looking at ways to mitigate our emissions while we're moving over to renewable energy.
So this isn't such a crazy idea. In fact, carbon capture is done in industry currently. The cheapest and most industry standard option is to use liquid amines to capture CO2 through a reversible chemical process. You can see the reaction mechanism here. Liquid amines are used at the point where they cost about $66 per metric ton of CO2 that's captured in order to remove it from whatever flue gas is flowing through the system. The reaction is then, like I said, reversible, so you can strip the CO2 back out and send it to a place for permanent sequestration or for sale as a byproduct. Now, there's a few issues with this because liquid amines are toxic and corrosive. They are very hard to handle in large quantities, especially the large quantities that would be required for a process such as this. And they require very high energies to be put into the system in order to remove the CO2 back from the reacted products. Metal organic frameworks, on the other hand, they rely on a physical adsorbance system or process. They are typically non-toxic, and there are no chemical byproducts that occur from this adsorbance. And even further than that, because it's physical rather than chemical, a lot less energy has to go into removing the CO2 from the system. So, kind of what is a metal organic framework? A metal organic framework is a class of compound that was synthesized more or less 20 years ago. After the past 2 decades, it's received a lot of attention because of some very unique properties. Here's a generalized structure. These green spheres are metal ions. They could be copper, zinc, magnesium, just about anything that has multiple d orbitals. And then these linkers here are some kind of organic compound. Now, metal organic frameworks are very tunable, which means that you can kind of adjust their properties based on exactly what you want. For example, if I want a certain catalyst, I would change out the metal ion center from copper to zinc. Or if I want different pore sizes or pore size distribution, I could change the organic linkers to get that. All metal organic frameworks have very high porosity and very high surface area. HCUST1, as an example, has 2,000 meters squared per gram of surface area for a given material. So there's a lot of potential applications for these, including gas capture, catalysis, drug delivery, et cetera, et cetera, et cetera. So the metal organic framework we're going to be focusing on for this presentation is HCUST1. HCUST1 was first synthesized by the Hong Kong University of Science and Technology in 1999. So it was one of the first metal organic frameworks synthesized. So there's a lot of data out there for it, both kinetic and non. It is a composite of the BTC ligand, which is the deprotonated version of what's called trimesic acid, and copper ions, some basic copper salt. It's synthesized as you mix the salts and the acids in a mixture of solvents and heat it in a reactor. So here is the general structure. You can see these cubic pores. They have a very high affinity for gas capture. So this particular MOF has shown a lot of promise for gas capture, and specifically CO2 gas capture. So the technological novelty associated with this project, MOFs are typically associated on a bench scale. Rachel and I have plenty of experience synthesizing these for R&D lab scales, where you're spending hours and hours and hours making less than a gram of MOF at a time. And that's just completely impractical when you're looking to use this in an industrial setting. So we're proposing the the development of a continuous scalable process to produce MOF on the order of kilograms per minute rather than milligrams per hour. We are focusing on the carbon capture market because there's a lot of data and a lot of evidence suggesting that MOFs would be a strong candidate for future carbon capture technology, and no companies are currently offering this solution. The specific carbon capture method we'd be suggesting would be a tower packed with MOF next to, say, a power plant, where the excess flue gas from the power plant could run through the tower, and the MOF would capture the CO2 for later sequestration.
So kind of moving towards what does that mean for us? We've decided to incorporate as an LLC, and we've decided to title ourselves MOF Solutions. A big goal of ours is obviously self-sustainability and looking towards a greener future. A very big concern is that right now we are in dire straits of can CO2 emissions and global warming be reversible? While we would really like to strive to hopefully make that a reversible process, we would at least presently like to mitigate these current circumstances. So a lot of our practices are centered around these core green ideas. So kind of introducing our business plan. As I mentioned, we'll be incorporating as a limited liability corporation, or LLC, particularly in Texas, mostly because of the strategic advantage to being near where a lot of fossil fuel combustion and oil companies are located, as well in the general Gulf Coast area. Particularly, as you see in Figure 6, we'd like to focus more in the Pasadena area. Again, we'd have great access to the larger Gulf Coast area, but we'd be strategically placed to hopefully try and secure an initial investment from one particular investor in that area. Again, we'd like to offer a scalable, continuous process that would be used particularly for one investor exclusively. Currently, they release about 112,000 metric tons of CO2 annually. We'd like to reduce that down by 89% to about 100,000, reducing 100,000 of CO2. So particularly, we'd like to focus on Albemarle Corporation. Again, they're located in Pasadena, Texas. One great benefit to Albemarle is that not only do they have this domestic location here in Texas, they have other locations spread throughout the U.S. and as well as international regions towards a future branch.
So the first step for this whole project was kind of developing a reactor system that could produce this amount of MOF. Like I said, we're used to producing grams and grams of MOF at a batch scale. So we had to take this data and extrapolate it forward to see how we could synthesize this in a continuous stirred reactor. So we found kinetic data from Hawk that fits certain parameters at certain temperatures to the Avrami kinetic model. This alpha is relative crystallinity, which is essentially an inorganic way of saying extent of reaction that kind of dictates how much of your reactants have crystallized into a particular system. So we were able to use this as kind of an extent of reaction equation. If you guys go into that packet that was handed out, you guys will see all of the math that we went through to calculate everything. I'm not going to talk about all of it because it is pretty boring. But the main takeaways is that we were able to calculate the maximum space-time yield of a particular reactor that shows the maximum mass product per unit of time per unit of reactor volume. So we got 19 grams per minute per liter of reactor volume at 125 degrees Celsius, which we were able to extrapolate further. We used the Dom-Kohler number for the system to try to hit a relative crystallinity of 50% after the reactors we chose, in order to make sure we weren't throwing away too many reactants. And we're able to identify a process that used a 42.7 liter reactor first, followed by a 962.7 liter reactor second in our system.
So throughout our process design, we had several iterations. As you can see here on the left is our main competitor, liquid amines, which again can be produce fairly cheaply, but at a cost of toxicity and as well as that high energy input in order to get the CO2 back. So our first process iteration, you can see here in this middle column, was MOF sequestration. So essentially what we were planning on doing was producing the MOF completely continuously, using it to capture the carbon and then either burying it or destroying it some other way. And obviously that comes at a really high cost as well as a high footprint for the plant. So in order to do that model, we had to be synthesizing on the gigaton scale, which is not physically or economically feasible. So we stepped back a little bit and reevaluated our process, and that's where we're at now with our third iteration, so MOF capture. So like Chris had gone over a little bit, we'd be essentially synthesizing a set amount of MOF, and we'd be storing it in two different towers where the CO2 would be directed to these towers. The MOF would absorb the carbon dioxide, and when that MOF is fully saturated, it would be the CO2 would be stripped off, and the MOF could actually be reused. So that's going to significantly decrease the amount of MOF that we have to produce in the first place, so our scale, as well as lowering the price. And right now, our price is around $46 per ton of CO2 captured, and we'll go into that a little bit later on and how we calculate that in the economics. So this is our final process. This PFD is also in the supplemental material that we have passed out if you'd like a closer up look. So essentially our process involves 6 different unit operations. So dissolution, reactor crystallization, filtration, go into solvent recovery, and then solvent exchange, and activation and storage. So each of those blocked off unit operations is also a different PNID in, again, the supplemental material that we passed out. And that each of those PNIDs have a fully developed process control system based on level pressure and temperature limits, as well as set points that we need for our process. And Sara will go into a little bit later on in terms of how that is being used for safety. So essentially our process starts off with dissolution. So that starts off with our 2 reactants, so trimesic acid, as well as copper nitrate trihydrate. And that gets mixed into our 1:1:1 volumetric ratio of our 3 different solvents, so ethanol, DMF, and water. And that goes into our 2 CSTRs, like Chris had mentioned, and then so forth into storage, and then it will be packaged and shipped to the Bay Point plant.
So due to time and budget constraints, we decided to have a purely theoretical model. We decided to model our process using Aspen Plus, but due to limitations in the system itself, we decided to focus solely on solvent recovery and the loop encompassing it, with a focus on these 2 distillation columns here, which separate out the solvents back into their pure components. So the main issues was just that Aspen Plus version 10 is meant for fluids and petrochemicals, and we're dealing with 3D crystalline structures with metal corded ions, and Aspen just doesn't have the capabilities of handling or modeling these materials, especially when it comes to novel chemicals not in their current database. So we were unable to model the reaction either. So instead, our goal of the model was to size our 2 distillation columns, with the first one, C001, separating out the ethanol being considerably larger than the second one, which separates out DMF and water. And from there, we were able to estimate utility and heating requirements and the required temperatures and pressures to run at, so we could determine our safe operable ranges for these processes. And we could also get a decent economic estimation of what these 2 distillation columns would entail, because other than the reactor, these were assumed to be our main costs incurred for equipment. However, they are going to be estimations because they lack the DMF wash from the solids processing downstream.
So on the topic of safety, of course, it's a big consideration to look at safety. In your additional supplemental packet, you will see the full HAZOP analysis. On the screen is a brief summary of our four main ones that we'd like to focus on. As well, you'll see in the packet the SDS summary. So if you take a look at that, you'll notice that we work with a lot of solvents, and that was a big reason why the modeling in Aspen was only soluble thermal, just because that will incorporate most of what we are concerned about in safety, particularly in pressure, temperature, and level. Throughout our system, we do have some manual inputs of operators incorporating in some of our solid materials, so we do need to acknowledge that in our safety procedures. Particularly, that would be coming into Mixer 5, where we have the total volumetric proper incorporation of all of our materials there. So of course, we wanted to really make sure that we're considering what proper automated loops do we need to have. We've also decided that because we're working with solvents, properly sized relief valves would be necessary, as well as oxygen sensors and ventilation throughout the facility, to make sure that anyone located in there would be aware of when they need to exit in the event that the oxygen levels are beginning to dip because of an accidental release of solvents. As well, in the design actions, you'll see where we try to reflect certain actions on our P&ID, and in the safeguards, in the event of level, we did try to incorporate secondary containment, just because some of our materials can be toxic and corrosive in the very initial phase, so we didn't want that to enter into the larger environment and therefore affect our neighbors around us.
So switching gears a little bit, excuse me, to economics. So we initially calculated our fixed capital costs. So as you can see here on the right is a summary of all of our major equipment costs, with the distillation columns being the most expensive, which makes sense because those are the largest vessels that are currently in our process. And to totally understand the capital costs, we have to calculate the ISBL, which is the inside battery limits, OSBL, which is outside battery limits, design and engineering, and contingency costs, which all add up to our total capital cost estimate of $13.2 million. So next we calculated the production costs. So our total cash cost of production would be about $10.8 million, and that composed of the variable costs and the fixed costs. So variable costs are generally things like raw materials, waste disposal, packaging and shipping, utilities, and the fixed cost is generally labor costs, supervision, overheads, things of that nature. And as you can see, our utilities are the highest percentage of our variable costs, around 70%. And normally raw materials are, but our raw materials are a little bit lower just because we have that solvent, solvent recovery. And all of the calculations, both for the capital costs and the production costs, were calculated via assumptions derived from the chemical engineering design textbook that was used in Capstone 1. So to understand the revenues, margins, and profits a little bit more, we made a few assumptions. So it was assumed that there would be a 5-year recovery period, a 21% tax rate, which is generally the tax rate for LLCs, a 15% interest rate on our investment, and a 20-year plant lifespan. So to understand how we price things, I'll direct you to this table over here. So because there aren't any other large-scale MOF producers on the market right now, we didn't have anything to compare it to in terms of pricing. So what we did was we took the total amount of MOF that we would be producing, so 613 tons on an annual basis, and we calculated the selling price that we'd have to sell that at in order just to break even, so break even on the capital costs as well as the production costs. So we wanted to choose a selling price that's obviously over that, but one that is competitive with liquid amines and would give us obviously a profit. So we came up with a selling price of about $37.5 thousand per ton, which comes down to $46 per ton of CO2 captured. Now this is $20 less than the current price for liquid amines, so it is competitive. And that would give us a total net profit of about $9.6 million. And over that 20-year plant lifespan, our net present value would be about $48 million with a discounted cash flow rate of return of about 80%. Now, what that discounted cash flow rate of return is is basically the highest interest rate that we could be paying and still turn a profit after those 20 years. So 80% it's still very high, which shows that we have a very profitable process right now. And given all of that, given our cash cost of production as well as our capital costs, we would need an initial investment of around $25 million.
So we as MOF Solutions set out to make an economically feasible, continuous process to scale up MOF production from its batch lab scale. And we plan to reuse our MOF throughout its 5-year lifespan in order to maximize efficiency and reduce potential costs incurred both to us and our clients selling it for $46 per ton of CO2 captured, which is economically competitive compared to liquid amines. We will capture 100,000 tons of CO2 annually at the Albemarle power plant with the goal of capturing approximately 89% of their emissions annually. So there's still a lot left in terms of work for the future. Oh my gosh. Sorry. First, we're going to find a simulation built for crystalline solids, just so we can model our entire plant in full and get a better idea of our estimated costs for equipment, installation, utilities, heating requirements, etc. And we also want to do a lot of physical chemistries to refine our data. We want to create a pilot plant, CSTR, in order to compare it to the theoretical kinetic data that we've collected from various papers, and in order to estimate our heating requirements, how long our solvent will last, etc. And we also want to do tests on the MOF longevity, just because right now, due to the novel nature of our product, there's not a lot of implementation studies done. So we want to know how being in the flue gas environment for prolonged periods of time will affect our product, because there has been some studies shown that water degradation may occur. And before we take any questions, we'd like to take a few minutes to thank a few people. To Katie Pacino, thank you for all of your feedback and all of your patience with reading our reports. To Professor Ronald Willey for his assistance with the HAZOP and our safety considerations, and to Professor Courtney Pfluger for being there every step of the way, helping us create an effective, feasible project.
Questions? Steve?
I imagine it's a lot, but do you guys know like what percentage of total CO2 emissions come from like the types of plants that you guys are going to be targeting?
So we don't have a specific percentage. However, just for an example, so the original plant that we actually looked at was called the W.A. Parrish plant, which is also in Texas, and it itself is one of the largest producers of CO2 in the United States, and it produces about 20 million tons of CO2 a year, which is much higher than obviously the plant that we chose, which is about, again, about 100,000 tons. So it's a significant amount.
Yeah, we decided to go with Albemarle just because it was a smaller plant, and we found it more reasonable to start off small, and then when we have a proven concept, we could move to larger plants.
But this data was gathered from an EPA database, so it's actually an interesting tool where you can kind of sort based on emissions, so that might be a good resource.
So I know there's like an index of greenhouse gases and their effect, the warming effect. I don't know where, I forget if it's CO2 or methane that's like a 1 and everything else is a multiplier of that. Like
Yeah, so CO2 is a 1 and
CO2 is a
methane's
1.
like
So,
20.
Yeah, so methane's 20, CFCs are like 1,000 times that.
Yep.
Have you thought about targeting one of those gases since you'd be 100, 1,000 times more efficient, something like that?
Yeah, so a lot of different MOFs do have an affinity for other gases. So just as an example, the MOF that we looked at previously to HCAS1 was called MIL 53, and it was an aluminum-centered MOF, and it actually had an affinity for nitrogen, which is not terribly helpful for for greenhouse emissions. But there is other applications right now for MOFs for different gases. The reason we targeted CO2 was just because we had an implementable way of implementing our project. So because these plants, the main greenhouse gas is CO2. And we would have a way of directing it to our MOF to absorb. That's why we targeted CO2 in the first place. But there's definitely a market for capturing other greenhouse gases.
And keep in mind, the point of this project was to develop the process, so this can be tailored to other products.
Mm-hmm.
In your next to the last slide there, you talked about finding a simulation system. I guess I would suggest you're never going to find that. So, what's the alternative? And the alternative on things like that is to create a process development program. And so, I think that should be a component of the next steps. And having said that, that has a cost, usually a big cost, and often a lot of time, and time is money also. So you did a great job in the design, you did a great job in the economic analysis, and you justified going forward. So I think in the economic analysis, you might want to add in some kind of an estimate of what that development process is gonna take. How much money?
Yeah, definitely. So for right now, it was a little bit outside of the scope of this project, just because we wanted to limit our scope down to mainly the design aspect.
Yeah.
But again, like Rachel had mentioned, we do want to do a lot of those scale up and experimental data gathering in order to in that kind of research and development phase in order to get to what we've designed right now. But that's definitely, again, something you're right, we could look into, but in terms of the economics for right now, it was out of the scope.
Any freedom to operate issues?
Sorry, freedom to operate.
Yeah, intellectual property, freedom to operate issues?
So there's not a lot of patents out. There's one patent that I found doing several hours of digging that pertains to continuous MOF synthesis, and that is specifically using solvents and other materials at critical properties, with supercritical fluids. This is a process that occurs at relatively mild temperatures at non-critical points. So this falls out of the scope of that patent, and there's only 2 other companies in the world that claim to be working on continuous MOF production, and both of them are startups without any specific IP out there. It's all their own thing.
Yeah, and in some cases there was an additional patent where it was a solventless process, but based on our chemistry,
that one.
we can't compete with that, just due to our chemistry alone.
So you're thinking of having big packed columns.
Yep.
What do you know about the structural integrity of the MOF? Can you put it into a big packed column and not have it crush? I don't have any feeling for that.
Who did the pelletized research?
Oh, I did. Yeah, so again, that wasn't something that we totally had dived into, but in my research, there are there's some research being done in beads. So you would conjugate this MOF to these basically plastic beads, and then you'd be able to pack it in terms of and be able to pack it and it would be stable. But like Rachel had mentioned, we do, if we were able to do any future work, we would like to do stability testing in terms of degradation and even maybe some structural experiments.
Yeah, it's a crystalline structure, and when we pelletize it, it would be pretty similar to a packed bed reactor.
I'm gonna kind of sort of piggyback on that, which is you said you would reuse the MOF. chemistry is behind that, and someone do A, and B would be, where would you, store this?
So,
As a physical absorbent, the chemistry of the MOF is not changed at all when it captures CO2. It's simply like stored in the pores.
Yeah.
And that's also one of the nice things about MOFs, how you can like change pore size and change like polarity and affinity to try to attract specific kinds of gases, in this case CO2. So in this case, it would just be like captured within the pores, and then we would have an inert purge gas to release the CO2 for reuse. So we'd have one tank purging while the other one collects our emissions. And of course, what to do with CO2 is definitely an issue. Currently, in the beverage industry, they mine for CO2. So this could be used as a replacement for that. WA Parish, one of the only carbon capture plants in the US, uses their CO2 for fracking, which is not ideal, but is a use. There's a relatively new startup over on the West Coast called Carbon Engineering, who claim that they can make a synthetic fuel out of CO2 and then have a like carbon neutral fuel, essentially, since you're just using CO2 that has already been released into the atmosphere in their like fuel. So there's a couple different aspects, but it's definitely something to look into and may change based on the plant.
At the risk of lecturing, what you've done is a great example of having done the preliminary technical and economic analysis for a new process. When you go into industry and you're working for a company or you're working as an entrepreneur, the first thing you want to do is demonstrate that the process is economically feasible. And this is what you've accomplished. And that was as I see it, the scope of what you were doing, and you did a great job at it. The first boss I ever had in a research and development facility, when I proposed the process to him, he said to me, "Show me the technical and economic analysis before you can go into the lab and do a test." That's how strict he was about it. Because in industry, you got to work on things that are profitable, and to position yourself to be doing good research for that company, you want to be able to demonstrate the profitability. So you've done a great example here of what the first step needs to be in any overall development process. After that comes, lab tests, pilot plant testing, prototypes, all of that comes after that, and all of that has a cost. But it all starts with what you've done here.
thank you.
Thank you.
So I know there's been talk in the past about maybe implementing a carbon tax, and regardless of whether or not that would happen, have you looked into how that might affect the economics of this process and at all?
So if, let's say there was a carbon tax, a lot of companies would be a lot more invested in purchasing some type of carbon capture system. They would be trying to offset the cost of the tax versus the cost of implementing the system to remove CO2 from their process. So there would be a lot more demand for this. Right now, we're partnered with just one power plant. Theoretically, would be partnering with just one power plant. But if there was some kind of widespread carbon tax that went into effect, a lot of other companies and power organizations would be interested in something like this. So we would get very popular very quick. Lucas?
How do your costs compare to having a power plant switch to any sort of renewable fuels that are carbon neutral? Can you compete against something, for example, like solar energy?
Beyond the scope of the project is what I would say.
I do want to add to that. So a lot of those renewable energy sources are very expensive right now, and at the scale that we'd be looking at, so at a national provider of power like this plant is, it'd be very highly economically infeasible for them to fully go renewable. That's kind of the main issue with renewables right now. So we're providing an option to implement something to help them so they don't have to fully transition over to, they can kind of be more stable, if that makes any sense. That's just my addition.
Yeah, that's fair. It's kind of a stopgap measure until we get to full renewables, which is the end goal eventually.
We good? Go ahead.
I think you touched on this, but what do you think the likelihood of other combustion products interfering with the efficacy?
It would be high. There's definitely, especially water vapor, is known to have an effect on metal organic frameworks. So figuring out if you would have to dry the flue gas first before running it through the column, or figuring out if there's other side products that could affect the performance, that there would have to be a lot of lab scale testing that goes into that.
And probably additional scrubbers or something else to kind of filter out some other particulate.
Yeah.
They do that with methane,
Yep.
right?
Yep.
They filter it and they take out all the.
Clean coal.
Don't even get started.
Methane's natural gas.
Yeah. All right, excellent. Thank you very much.